we'd like to come up with a series that would represent the function e to the x. And broadly, this is called a Taylor series. And specifically, there's a certain kind of Taylor series called a Maclaurin series. And a Maclaurin series is centered at x equals 0. The Taylor series is centered at x equals a. So Taylor series is a series, polynomial, that can represent some other function, and it happens to be centered at some point. Maclaurin is a specific Taylor series that's centered at x equals 0. And the main issue here for us is, as we're coming up with our series and our polynomial, is just paying attention to how that's done. So some notation for a general rule. A polynomial of degree n in terms of x that will represent some function must follow this form. It will first be f of a, the function's value at a, plus the value of the function's derivative at a over 1 factorial times x minus a to the first, plus the function's second derivative at a over 2 factorial times x minus a x minus a squared. Hopefully you're starting to see the pattern here for the next one, times the function's third derivative at the value in which we're looking over 3 factorial times x minus a cubed. Right, and the purpose of this is so that the function we're creating, the polynomial we're creating, will match up with the function in question at the function's value, and in terms of the derivative and second derivative and third derivative, and to whatever degree of accuracy we want. And we'll continue on to the nth derivative of our function at a over n factorial times x minus a to the n power. This will be our polynomial that will model some function. And so as an example, we're going to work on a function f of x equals e to the x, and we will center it at x equals 0, which means we're specifically going to create what's called a Maclaurin series. F prime of x, and we'll do the first 4 terms, happens to equal e to the x. And this is nice. F double prime of x is also e to the x. And the third derivative is also e to the x, which makes this a nice place to start. Notice that f of 0 equals 1, and so does f prime of 0, and the second derivative and the third derivative happen to all equal 1. Which again makes this a nice place to start. So our polynomial that will be third degree of x will be the value of the function 1 plus the value of the function's derivative over 1 factorial times x minus 0 to the first, plus the value of the function's second derivative over 2 factorial times x minus 0 squared, plus the value of the function over 3 factorial times x cubed. So this is our third degree polynomial, and this we're using as an approximation for e to the x. Now if I were to simplify this, this would be 1 plus x plus 1/2 x squared plus 1/3 x cubed. And we're saying that that is about e to the x. Now if we were to test this for some value of x, like x equals 1, we find that this expression is 2.718 and this expression is 2.833. It's a decent approximation, right, for x equals 1. You might say, well, that's off by more than a tenth. I don't know if that's decent. Well, remember that we set this up to be centered at 0, so we're a decent distance from 0. What happens if we test a point closer to 0, like 0.1? And if we test x equals 0.1, or a tenth, we would find this expression to be 1.1053, and this expression to be 1.1052. So we've gotten closer to where we're centered at, where we would expect it to be more exact, and now we're off only by roughly a 10,000th. This is a good tool. And it's going to be more accurate the more degrees our polynomial has, and as we get closer to where we're actually centered in terms of how we constructed it. The big thing here is that you're able to construct a Taylor polynomial according to the pattern. Also notice that if we had continued on with our series and just kept writing it out, we would have eventually ended up at an nth term. Oops. Right, 1 over n factorial times x to the n. And so we can express this using series notation, right, that the function, I'll do it down here, the function e to the x is equivalent exactly to the series from n equals 0 to infinity of x to the n over n factorial. But if we were to add an infinite number of terms up, we would exactly get e to the x. One question someone has, well, what is 0 factorial equal? It's defined to equal 1. Right, so now we can represent functions like e to the x as series.